Today, we're going to pull back the curtain on one of the most powerful and most used buttons on your keyboard, undo. It really does feel like magic, right? But it's actually a super elegant concept that's running the show behind everything from your web browser to the very code your computer is running this second.
I mean, think about it. You've definitely done this. You're typing away, you make a quick typo, and without even thinking, bam, you hit undo, and instantly your computer knows exactly what you just did and reverses it. But how? How does it know? Well, it's not magic. It's a brilliant piece of computer science that we're going to unpack right now.
So the secret sauce behind that mystery is a surprisingly simple, yet incredibly powerful idea called a stack. And this isn't some high-level abstract theory. Oh no, it's a practical tool that is working hard for you right now in your browser, in your text editor, and even in a lot of the video games you play.
Okay, so what is a stack? At its core, it's just a collection of items, kind of like a list. But it has one very, very strict rule that gives it all its power. Last in, first out. We call it LIFO for short. All it means is that whatever you put in last is the very first thing you have to take out. That's it. That is the whole rule. And this slide gives us the perfect real-world picture, a stack of cafeteria trays. Imagine you put a clean tray on top of the pile. In the world of programming, we call that a push. Then, someone else comes along and pushes another tray right on top of yours. Now, the next person in line needs a tray. What do? They can't just grab one from the middle of the stack, right? Nope. They have to take the one on top, the last one that was just added. And we call that action a pop. So, push to add, pop to remove. Super simple, but as you'll see, incredibly powerful.
All right, so now that we've got this idea of push and pop down, let's see how it connects back to our original question. We'll start with the most obvious use case, basically going back in time.
And I guarantee you have seen this in action probably dozens of times already today. That undo button? Yep, that's a stack. The back button in your web browser? Total stack. Even a character in a video game trying to find its way out of a maze? All of these things rely on the exact same simple logic of backtracking.
Just think about it for a second. When you're working on something, you're performing a sequence of actions. You type a word, that's action 1. You make that word bold, that's action 2. You insert a picture, action 3. Your computer is quietly keeping a record of this history, one action right after the other.
So here's the big question. Why is a stack, with its whole last in, first out rule, the absolute perfect tool for managing this history?
And boom, this is the answer. It's so elegant. When you hit undo, you don't want to get rid of the very first thing you did an hour ago, right? Of course not. You want to undo the very last thing you just did. The last action you put in must be the first action you take out. It is a natural, perfect match for the LIFO principle.
Okay, so we've established stacks are amazing for going backward. But get this, they're also absolutely essential for making sure things are built correctly in the first place, especially when we're talking about the language of computers, code.
You see, the programs that translate our code into something a computer can actually understand are called compilers. And compilers use stacks all the time. One of their most important jobs is just checking for balanced parentheses. As you can see on the slide, every single opening bracket has to have a matching closing bracket in exactly the right order, otherwise the whole program can just fail.
So let's just walk through this process. As the computer reads the code, it sees an opening bracket and push. It puts it onto the stack. Then it sees another opening bracket and push. It puts that one on top. Now when it finally hits a closing bracket, it doesn't add anything. Instead, it pop, removes the last opening bracket it saw. It sees the final closing bracket and pop, it removes the next one. At the very end, if the stack is totally empty, it means every single bracket had a partner. The code is balanced. Perfect.
And that's the whole point. These nested structures, they rely on this rule. The most recently open bracket has to be the very first one to get closed. And once again, last in, first out provides the perfect logic for the job.
All right, now we're going to go for the deepest application of them all, because stacks aren't just some handy tool for specific tasks. They are fundamental to how computer programs actually run and manage their memory, and this is called the call stack.
The call stack is basically the engine room of all computing. It manages which piece of code is currently running, it helps figure out complex math problems, and it even sets aside memory for all the little bits of information a function needs to do its work. Just picture any computer program. It starts with a main function. That function then calls another helper, let's call it func1, to do a specific job. But maybe func1 needs its own help, so it calls func2. All of a sudden, you've got this chain of functions, each one paused and just waiting for the next one to finish up.
So here's the puzzle. When Func2 is finally done with its job, how does the computer know to go back to Func1? Why doesn't it just jump all the way back to the main program? How does it keep everything in order and not get lost?
And by now, you've probably guessed it. LIFO. The last function that was called, Func2 in our case, must be the first one to finish. As soon as it's done, it gets popped right off the call stack, and the program's control goes right back to Func1, which was waiting just underneath it. It's a system that ensures a perfectly orderly execution, every single time.
So, we've seen stacks in action for undoing, for checking code, and for actually running our programs. Let's bring it all home with one big, clear idea.
Just look at the pattern here in this table. From function calls to undo buttons to checking syntax, all of these very different problems share the exact same underlying logic. They all need a structure where the last item added is the first one that needs to be dealt with. And that, my friends, is the real power of the stack.
This is really the key takeaway. If you ever run into a problem where you need to manage a sequence of things, and the core logic involves reversing, or backtracking, or undoing the most recent step, a stack is almost always the most elegant answer.
So after all of this, if there's just one thing you should walk away with today, what is it?
It's this. The next time you hit undo or you click your browser's back button, you'll know the secret. You'll know it isn't some kind of digital magic. It's the simple, elegant power of a stack, working silently behind the scenes to make sure the last thing that went in is always the first thing to come out.